that brings us to the third section on advanced numerical integration. So, there is some very, very clever math, not surprisingly thanks to Gauss, who is able to give you the answer to accuracy 2n minus 1, keeping the same n points. Right? It seems impossible. How is it possible? Right? So, the next few slides will try to understand how we can get an accuracy of order 2n minus 1, keeping the same n points. Okay? So, we will sort of go through it step by step. Everyone with me so far? Objective is find out the integral of a function as accurately as possible when I do not know the analytical integration of this function. Okay. Now, there is something called as the inner product. Right. So, if I give you two vectors over here, say A and B with some angle theta between them, we all know the inner product of these two vectors is, what would you write it as? A transpose B, right. So, in the language of linear algebra, I will write this as A transpose B. In the language of vectors, I will write this as, right, both mean the same thing. Now, so this is about inner product of vectors. How about inner products of functions? How do we take inner products of functions? That is the concept that we will need further over here. So, the dot product, element wise dot product, it generalizes to a integral, right. So, if I say two functions, say f of x and g of x, I want their inner product, right. So, the symbol is f comma g and its value is given by a definite integral of f x g x dx. Okay. So, in the case of inner product of vectors, you could have the inner product of, supposing I ask you the inner product of two non-zero vectors, supposing it is 0, what does that tell you? Their vectors are perpendicular to each other, right. So, inner product 0 when the two vectors are non-zero themselves means that the vectors are orthogonal to each other. If I tell you two non-zero functions have inner product 0, the same terminology applies. We say that these two functions are orthogonal to each other, right. So, if f comma g is equal to 0, then f g are orthogonal. You can no longer visualize it as two arrows in space, okay, but that is the price you are paying for some abstraction. Now, you have abstracted the idea of a dot product from vectors to functions, okay, and you can talk about orthogonality. All right. So, this so called Gaussian quadrature that we are discussing now, it starts with saying construct a polynomial of order n, okay, such that it is orthogonal to all polynomials of order less than n. So, this x to the power k over here, notice that k is maximum n minus 1. If you can take k equal to 0, that means the average of Pn is 0, then I take x square all the way up to xn minus 1. Okay. So, what you do is you construct a polynomial of order n such that it is orthogonal to all lower orders of polynomials. Okay. How would you do this? We can again go back to how we had done this process with vectors, right. In vectors, supposing I gave you a bunch of vectors like this, let us say in 3D space v1, v2, v3. Okay. Let us say these three vectors are in 3-dimensional space, and I said that given these three vectors, can you construct a set of 3 vectors which are all orthogonal to each other? You can, right. Gram-Schmidt process, right. So, Gram-Schmidt process is what you would follow. You would take one vector, keep that the first vector, subtract off the part of the second vector along the first vector, you get the next vector, and you repeat this process in n steps, you get n vectors that are all orthogonal to each other, right. So, those of you who have not done linear algebra, you can revise this concept of Gram-Schmidt. This same process I can apply to functions, because the concept of dot product or orthogonality holds true for functions also, right. So, I can start with 1 x, x squared, x cube, all of these guys. Okay. So, supposing I take 1 x, x squared, okay, and I give you the interval of -1 to 1. Okay. So, is the function say is 1, so f 0 x is equal to 1 and f 2 x is equal to x square. Are these two orthogonal to each other? Let us find out. So, if I do this f 0 x f 2 x dx -1 to 1 is equal to, so -1 to 1 x square dx is equal to x cube by 3 -1 to 1, and the answer is right. So, these two functions are not orthogonal to each other, but there is no problem. I can apply this Gram-Schmidt process and I can arrive at a set of functions that are polynomial functions which are all orthogonal to each other. Okay. This has of course been done, and there is a very nice name for these polynomials. These polynomials that you get after orthogonalization are called so-called Legendre polynomials. Okay. There is an entire family of orthogonal polynomials with different names and different properties, but the idea is the same, orthogonality between functions. Okay. So far so good. So, what is our sort of summary of step 1 is I have constructed a set of polynomials which are orthogonal, right. So, if I fix my n, I have created this p and x over here orthogonal to all x to the power k. Okay. Now, how will we use it? Let us see. That takes us to step 2. Any questions? Clear, right? Okay. Now, step 2, what are the roots of this polynomial function? I am not asking a very specific question. Okay. I am just saying how many roots will there be of this nth order polynomial? First order polynomial, how many roots or zeros? Call it zeros. How many roots does it have? At max n. No, say n, they can be repeated roots also, right. X minus 2 whole squared, 2 is repeated twice, right. So, there are n roots. Okay. By roots, what do I mean? The places where the function goes to 0, right. So, p n of x I is equal to 0, fine. There is a nice theorem from numerical analysis which we will not prove over here, but it says that for orthogonal polynomials, the roots are always real and distinct. We will just use it. Okay. So, for orthogonal, real and distinct roots. All right. Okay. So, some of you must be wondering where is this discussion going. So, let us try to bring it closer. So, remember our function is f of x, which is not polynomial, it is some general function. Okay. Now, we want to try something interesting. We want to try to approximate it by a polynomial of order 2n minus 1. Okay. So, suppose let us just jump straight into the example. Okay. So, this example over here, the numerator is a polynomial of order 3, it's a cubic polynomial, denominator is a polynomial order 2. So, this is actually goes back to something which you would have done in high school. It is called Euclidean division of rational functions. If I do this division, this is order 2, this is order 3, the quotient will be order 1, right. So, that is this guy over here, and the remainder will also be of degree 1 in this case, right. So, the same thing applies over here. I will get a qx, okay, plus I will have some remainder rx, right. But what is the special property of qx and rx? Q and r, what will their order be? N minus 1 at most, because I have divided by polynomial of order n and I want the function approximation to order 2n minus 1. So, the best that you could do is q can at best be order n minus 1, right. So, order less than n. Okay. Right. So, that is if I just open out this formula over here, I get f 2n minus 1x, that is the approximation to order 2n minus 1, as a qx multiplied by pnx plus rx. Okay. That is your Euclidean division. Now, what do you think would be next? Yeah, I removed the denominator, right? In this expression over here, I just multiplied p and x on both sides, right? So, I have a quotient and I have a remainder over here. What was our ultimate objective? Integrate the function, right? So, we have done some weird looking manipulation. Next, let us try to integrate and see what happens. Okay. Takes us to step 4. We are going to integrate on both sides of this expression. Okay. So, I am going to integrate this whole thing. Okay. Remember, these are never indefinite integrals, these are always definite integrals. Okay. We are only talking about definite integrals. All right. So, can you tell me, let us look at the first term over here. Okay. When I integrate this guy, qx p and x, what do you think the answer will be? Answer has to be 0 because, okay, so qx is a polynomial of order, what was the order of qx? n minus 1, right. So, this was n minus 1. So, I could have written it like this, a0 plus a1x plus dot 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 up to a n minus 1 x n minus 1, and what is happening is being multiplied by p and x and integrated. But how did we construct these pn's? Orthogonal to every degree less than it. So, it is orthogonal to this guy, this guy, this guy, all of these guys. So, this integration goes to, the first term goes to 0. So, I am left with this integral as f2n minus 1 x dx from x1 to xn. This is going to be equal to x1 to xn rx dx. I cannot simplify this rx term anymore, it's right. It is of order n minus 1, but that is about it, right. I can't do anything else to it. But what do we have with us? We have n points at which I have a possibility of evaluating my function. Okay. So, supposing I were to use those n points, can I write this, can I simplify this further in terms of what we already learned? Can I construct a Lagrange polynomial for Rx? I can, right, because I have a expression for f2n minus 1x. So, I know q, I know p, I know r. So, I know Rx is some polynomial of degree n minus 1, right. So, I can use what we had discussed earlier, the Lagrange polynomials, to integrate this guy out, right. So, what will this integral be? Again very simple, I is equal to 1 to n. What should the first term be? I am integrating a function r. So, first term should be, I am using that the integration formula which I had derived, the quadrature rule which I had derived for Lagrange polynomials. First term should be the r of xi, exactly the value of the function at some node multiplied by the weights. So, wi, the weights do not depend on the function, right. So, remember these weights were given by the integral of Lix dx, right. That is what we had from x1 to xn, pre-computed. So, time is saved. Okay. So, I wanted the integral of this guy and I am somehow left with the value of some other function only. Okay. So far, have we specified the locations xi? No, right, we just left it general. Okay. So, now let us play the final card of tricks, which is step 5, is that if the n points are chosen to be the roots of p and x. Okay. So, what can I say about f2n minus 1 xi? What will its value be equal to? Right. So, it will be 0 because it is the root of p and x plus r of xi, right. So, putting this and this together, integral from x1 to xn f of 2n minus 1 x dx is equal to, now I will use this guy over here, but I can replace r of xi by, right. So, I can just replace, so anyway this was whole thing was anyway an approximation of x itself, right. So, this will become, so let us get this, so approximately I is equal to 1 to n f of x I w I. So, does this look like a quadrature rule? It looks like a quadrature rule. Why? Because the node values are to be given, the weights are given which are independently calculated. So, I have got a quadrature rule. Because of the extreme cleverness of both Gauss and Legendre, the name of Gauss-Legendre goes after them. So, you have a Gauss-Legendre quadrature rule which is accurate to order 2n minus 1, right. What was, did you have to pay a price for getting this very good result? We had to figure out P and X, but that is a one time affair. Any other any other price that I had to pay? Value of n will be? Value of n will be high. No, value of n is up to you. If you tell me that I have access to the function only at 4 points, then you will create P4x. It is in your hand how much accuracy you want. But when you choose n equal to 4, your answer is accurate to what order? Order 2n minus 1, which is 7. In the earlier high school approach, our answer was accurate only to order 3, right, for n equal to 4. Because earlier what we said, with n points I can fit a polynomial of degree n minus 1. So, my answer, if I give you n equal to 4, your answer is at best you can approximate a cubic function and integrate it. Now, you are saying with 4 points you can do a 7th order polynomial. Okay. The price that you have to pay is that you do not have choice on where to evaluate the function. You are forced to choose the xi's to be the roots of p and x. You can't just say I will uniformly chop up my interval at spacing h. You can't do that. You have to use the roots of Pn. Otherwise, what happens? This property does not hold true. Okay, but that's a small price to pay. So, in the case of these Gauss-Legendre quadrature rules, both the xi's and the wi's, these are pre-computed. There are mathematical libraries, MATLAB has it, C++ has it. Just invoke them. They will give you the set of x's and w's. Plug it into your thing and you're done. Okay. So, you will use these quadrature rules extensively in integral equation approaches. To drive home the idea of Gaussian quadrature that we have studied so far, what we will do is we will take a simple example, and the example that I have taken is a function f(x) is x plus 1 cube and the interval is minus 1 to 1. Okay. So, the choice of how many points of quadrature rule that I want, it is up to me. So, for example, this is the first Gauss-Legendre polynomial or Legendre polynomial, this is the second, and this is P2, right. So, P0, P1, P2. To just test our understanding, let us see if they are orthogonal to each other, right. So, if I take the inner product of P0 and P1, right. So, what do I get? Minus 1 to 1 x dx, and you can see that this is going to be 0. Okay. Let us take P0 and P2. Okay. So, minus 1 to 1, I will have 3x square minus 1 dx by 2. Okay. What am I going to get? So, half stays out over here, 3x cube by 3 from minus 1 to 1 and minus x by 2 from minus 1 to 1, right, and you can see that this will also come out to be 0. Okay. So, this shows us that our these polynomials are indeed orthogonal, and what remains for us to do is to evaluate this integral using, let us say, 3 different methods. So, the first example would be, for example, I mean we can take the exact calculation just to know what we are supposed to get. So, integral minus 1 to 1 f(x) dx, this is a polynomial function. So, it is trivial to integrate. So, I am going to get x plus 1 to the power 4 by 4 evaluated at minus 1 to 1, and that is going to give me 2 to the power 4 minus, so that is 0 by 4, that is going to give me 16 by 4, which is 4. Okay. Let us try a little bit more, a more expensive evaluation, but using an inferior rule, which is the trapezoidal rule, the extended trapezoidal rule. So, here the spacing between the points, so it is 3 points between -1 to 1. So, the spacing your h is actually just equal to 1. So, the 3 point trapezoidal rule will give me 1 into the value of the function at the first point by 2, then f of 0 and then f of 1 by 2, right. So, this evaluates to, so the first one is going to give me 1 into, so 0, at 0 its value is 1 and at 2 its value, at 1 its value is 2 cube by 2, right. So, that is 8 by 2 4, that gives me 5. So, you can see that the trapezoidal rule is already overestimating the exact answer and not by some small amount, 5 when the actual answer should be 4. So, that is a big change. Let us see what a 2-point Gauss quadrature rule gives us. So, as I have mentioned before, a quadrature rule is defined by the nodes and the weights. So, for if I choose a 2-point rule, right, so n is equal to 2, this is the function that I am going to take. So, I already know the nodes. I mean, look at this function, you can see that the roots of this polynomial are simply xi is equal to plus minus 1 by root 3, and some extra information is needed, those are the weights. In this case, I will just give you the extra information that the weights are both equal to 1. In general, they need not be, and you have to calculate it carefully. Okay. So, let us evaluate this over here. So, I am going to get, is going to be sum of wi f of xi, that is my general formula. So, it is going to be 1 into f at minus 1 by root 3 plus 1 into f at 1 by root 3, okay. And this is going to give me 1 minus 1 by root 3 cube plus 1 plus 1 by root 3 cube, okay. And we can evaluate this quite simply. So, a cube plus b cube will give me, a plus b will be the first term, which is going to be 2. Then I have a plus a squared minus 1 minus 1 by 3 plus b squared, which is 1 plus 1 by root 3 squared, right. And you can work through the math, you will get an answer 4 in this case also. So, just observe that what we did is, by using only a 2-point Gauss quadrature rule, I was able to get the exact answer 4, right. This should not surprise us, because we know that a 2-point Gauss quadrature rule is accurate to order 2n minus 1, right, 2n minus 1, and in this case n is 2. So, this is accurate to order 3. My given function over here is a cubic polynomial. So, this is no surprise, I got the correct answer because all the conditions are satisfied. So, this just shows you that you can get the same answer by having only 2 function evaluations in this case, whereas if you used a slightly inaccurate quadrature rule, even a 3-point evaluation gives you the wrong answer. Okay. So, hopefully this drives home the importance of using a proper quadrature rule. Right. So, this brings us to an end of this module on numerical integration, or quadrature as it is more popularly known.